Okay, we should be live. And in about 30 seconds, y'all will catch up with me there in the chat. Alright, so, oxidation numbers. Redox, reduction, and oxidation. It's a kind of chemical reaction, specifically where you add oxygen to a thing, more or less. Oxidation doesn't always mean adding oxygen to something, but often it does. Okay, this is why it's called oxidation, is because adding oxygen results in oxidation. So, for example, you start with methane here on the left, you add one oxygen, you end up with methanol. You were adding oxygens to the central carbon, I should say. One oxygen gets you to methanol. You add a second oxygen bond. Now the carbon is double bound to the oxygen. You add another oxygen, and then you add another oxygen bond. You just keep on going. More and more bonds between carbon and oxygen. And that is a form of oxidation. That's not the only way oxidation can happen, though. Okay. When we are discussing redox reactions, generally, we mean that something is losing electrons. Okay. It is hard to see for something like this, that the carbon is losing losing electrons to the oxygen. But it kind of is. Okay. In other reactions, it's easier to see. It's much more explicit that oxidation means the loss of electrons. Reduction is the opposite of oxidation, and it means something gaining electrons. And oxygen, when it reacts with things, usually gains electrons. It steals electrons from things. Okay. In that case, we call it reduction. We measure this explicitly using oxidation number. Oxidation number is not charge. It is related to charge. It is kind of a measure of how many electrons a thing has, related to the number of electrons it has in the neutral atom. It is a measure of charge in a similar way to how formal charge is a measure of charge, but it isn't actually charge. So these are the rules for the oxidation number. When you're looking at a neutral atom, or the neutral element, I should say, the oxidation number is 0. Okay, so don't forget Brinkelhoff here. Okay, so molecular oxygen, O2, okay, has an oxidation number of 0. Okay, so the element in its native state has an oxidation number of 0. If you're looking at a monatomic ion, okay, then the oxidation number will be the charge on the ion. So oxidation number is related to charge. But you also have to look at oxidation numbers for atoms that are parts of molecules or polyatomic ions. And in that case, it's not quite the same thing as charge. Okay. So when you're looking at a molecule or a polyatomic ion, the sum of the oxidation numbers. If you look at the oxidation numbers of every single atom, and you have to do that, you'll find that they add up to the total charge on the molecule or polyatomic ions. Okay. So, in that way, oxidation number is similar to formal charge, but it is still a very different thing. Now, these you're pretty much just going to have to memorize. Hydrogen will have a formal charge of either +1 or -1, depending on what it's bound to. So if hydrogen is bound to a metal, then it's a metal hydride, and hydrogen has an oxidation number of -1. Okay. If it's bound to a nonmetal, then it'll have an oxidation number of +1. Fluorine will always, absolutely always, have an oxidation number of -1. Never anything else. Fluorine is the most electronegative element out there, and it is always going to have, it always gets its way, gets whatever the hell it wants. It will always have an oxidation number of -1. Oxygen, the second most electronegative element, has an oxidation number of -2 most of the time. If you're looking at a peroxide, okay, remember peroxide is O2 2 minus, polyatomic ion, then each of the oxygens in the peroxide will have an oxidation number of -1. Okay? And thus, -1 plus -1 adds up to the charge of -2 on the ion. All right. If oxygen is bound to fluorine, then oxygen will do whatever is necessary to make fluorine happy. Fluorine is the god-awful boss from hell. Okay? You do whatever it takes to get fluorine to shut up. Now, halides, or I should say halogens here. In this case, halogen is the general term, remember, for the elements on the far right-hand side of the periodic table. Okay. So, here, that means chlorine, bromine, iodine. Okay. Okay. So, these are the halogens. And fluorine is its own thing. It's got its own rule. Chlorine, bromine, iodine, they typically are going to have a formal charge, an oxidation number of -1. Okay? The exception there is if they are bound with oxygen or fluorine. Okay? If they're with oxygen or fluorine, they'll do whatever it takes to make oxygen or fluorine happy. Again, these rules are going to take some practice, and they're not going to give them to you on the test. So you're just going to have to remember them. Okay? So let's go through a few examples. Yep. So first up, potassium chlorate. So potassium chlorate. Okay, there we go. KClO3. Okay. When you are finding oxidation numbers, you have to find the oxidation number on every atom in the molecule or compound, whatever you're looking at. Okay. So here we have potassium on the one hand and chlorate on the other. Okay. An ionic compound. Potassium is a monatomic ion. So monatomic ion, the oxidation number is the charge on the ion. Meaning that potassium, monatomic ion, charge on the ion is positive 1, so the oxidation number is positive 1. Now we come over here to chlorate. Okay. So chlorate as a whole has to add up to -1 because chlorate as a whole has a charge of -1. You'll never ever stop having to remember to memorize really your polyatomic ions. Sorry, just the way it is. Now we head back, we look at our rules. Oxygen is almost always -2, unless it's a peroxide or bound to fluorine. In this case, it's neither a peroxide nor is it bound to fluorine. So each of our oxygens is -2. Okay. So chlorine plus our 3 oxygens, each of which is -2, has to add up to -1. So chlorine minus 6 equals -1, meaning chlorine has an oxidation number of positive 7. So positive 7 on chlorine, -2 on oxygen. And when we add all of those together, feels wrong. No, not positive 7. I am slow today. Positive 5. 5. All right. Let's see if any of you caught that before I did. Okay. So, in any event, that is how you calculate the set of oxidation numbers. Okay? You just have to make sure they all add up to the right numbers. You can do it for a neutral compound like this, or you can do it for a polyatomic ion by itself. So let us take a gander at our next example, sulfuric acid. All right, so sulfuric acid, H2SO4. All right, so once again, we are going to have to depend on the rules to, just it'll work its way through. Okay. So hydrogen is going to be, looking at the rules, hydrogen is either positive 1 or negative 1. It's not bound to a metal. It's bound to a polyatomic ion. Balances out. Hydrogen is going to be positive 1. Hydrogen will very, very rarely, only rarely be negative 1. Only if it is bound directly to a metal. So, for example, sodium hydride. Okay. Hydrides are pretty rare. Hydrogen really, really prefers to have an oxidation number of positive 1. It can do negative 1, but it's really unhappy. Okay. So, be careful for hydrides. They might throw one at you just to screw with you, but it's fairly unlikely. So, moving on. Oxygen, once again, is going to be -2. So we have our two hydrogens, each of which is positive 1. And we have sulfur. And we have our 4 oxygens, each of which is negative 2. And our sulfuric acid as a whole is neutral. Oxidation number 0. So 2 plus S minus 8 equals 0. S is equal to positive 6. So note that 1 plus 6 plus negative 2 is not equal to 0, but 2 times 1 is positive 2, 1 times 6 is positive 6, 4 times negative 2 is negative 8, and that does add up to 0. Okay. So you have to look at it in terms of a collection of atoms, a whole lot of atoms. Okay. So next example, magnesium nitrate. This one is a little bit more involved, not excessively so. Mg NO3 2. Be aware that I am keeping an eye on the chat, so feel free to jump in with questions anytime you are feeling a little bit out of the loop. Okay. So, magnesium here is, why isn't what negative 6? Desiree. Why isn't the sulfur? H2SO4. The hydrogen was plus 1. Sulfur was, and oxygen was negative 2. 2 times positive 1. Sulfur 4 times negative 2 equals 0. 2 plus sulfur minus 8 equals 0. Sulfur minus 8 equals negative 2. Sulfur equals positive 6. Got to be careful about your algebra. Go through it step by step. All right. So back to magnesium nitrate. So again, we have an ionic compound, magnesium nitrate. Magnesium is a monatomic ion. Therefore, it's just going to be the charge on the magnesium. Okay. So Going back to our good old-fashioned periodic table, here's magnesium, second column from the left, alkaline earth metal, positive 2 charge. So when we look at this, okay, so magnesium, positive 2. Which means that nitrate as a whole is going to have to be, negative 1. So there are two different ways of looking at this one. You could solve the entire thing, trying to add up the magnesium and all the nitrates and all the both nitrogens and all 6 oxygens and say it all adds up to 0. That'll work just fine. Or you can solve it for the nitrate by itself. I'm going to go ahead and do both. Okay. Each oxygen is still going to be always negative 2. Okay. Well, not always, but most of the time. Oxygen is negative 2. So, our 1 magnesium, positive 2, plus our 2 nitrogens. Okay, remember, when you have the subscript on the outside, it applies to everything on the inside. So 2 nitrogens, and we have 6 oxygens. Each oxygen is negative 2, and our entire compound, the salt as a whole, is neutral. Okay. So positive 2 plus our 2 nitrogens minus 12 is equal to 0. 2 nitrogens is equal to positive 10. Nitrogen equals positive 5. So that is one way to do this. Okay. The other is to just look at the nitrate by itself. Okay. So nitrate is NO3 minus. Oxygen is still negative 2. Nitrogen is question mark. So in that case, nitrogen plus our 3 oxygens is equal to negative 1. Because the nitrate by itself has a total charge of negative 1. Therefore, the oxidation numbers of the nitrogen and the 3 oxygens has to add up to negative 1. So nitrogen minus 6 equals negative 1. Nitrogen equals positive 5 still. Okay. You get the same answer either way. Trying to point out that you can break this up into smaller problems. You don't have to look at the entire molecule as a whole. You can do that if you want, as we did up here. Okay. We looked at the magnesium and both nitrogens and all 6 oxygens for our total neutral compound. Or you can do like we did down here and just look at the nitrate by itself. Okay. That got us the exact same result. Either way, magnesium has an oxidation number of positive 2, oxygen has an oxidation number of negative 2, nitrogen has an oxidation number of positive 5. Okay. So, next example. We have phosphate. just the polyatomic ion phosphate all by itself. Which means, come on, brush. There we go. We are looking at sorry, not phosphate, phosphite. My bad. Phosphite is PO3, 3 minus. Okay. Like I said, we can look at polyatomic ions, we can look at ionic compounds, we can look at covalent compounds, which we'll do in just a second. So, oxygen is still going to be -2. If we were in class, I would have, insisted that you repeat that over and over again. It would have gotten tiresome. All right. So, oxygen is -2. Phosphorus is going to be what? Okay. So, our 1 phosphorus atom plus our 3 oxygen atoms has to add up to -3. So phosphorus minus 6 equals -3. Phosphorus equals +3. So calculating oxidation numbers can get a little tedious-ish, but it's something you're going to have to get good at for reasons we'll get to in just a little bit. We're going to keep on practicing these. So next up is chlorite. ClO2 1-. As per usual, oxygen is -2. Chlorine plus our 2 oxygens has to add up to -1. Remember, oxidation numbers add up to the charge on the whole kit and caboodle. So if it's a neutral compound, it adds up to 0. In this case, it's a polyatomic ion, adds up to -1. The phosphite was equal to -3 because that was the charge. That's the charge on phosphite. PO3, 3-. In this case, chlorite, it adds up to -1. So chlorine minus 4 equals -1. So chlorine equals +3. And finally, what we have here, our last set of examples is a huge collection of organic compounds. Organic compounds that you don't quite know yet. Okay? But we can cover those easily enough. Okay. So, methane is CH4. Then we have methanol, CH3OH. Let's see if I have enough room to write all these. Formaldehyde, CH2O. Formic acid, COOH. And then finally carbon dioxide, CO2. All right. So, all of these are neutral, meaning that the oxidation numbers have to add up to 0. Okay. I'll let you know right now, oxygen and hydrogen are going to be the same for all of these compounds. What's changing is the oxidation number on carbon. So, we start excuse me, we start with hydrogen over here on the left, has an oxidation number of +1. So our 1 carbon plus our 4 hydrogens adds up to 0, meaning carbon here has an oxidation number of -4. We come over here to methanol, okay, slightly more complicated. If you're wondering about the structure, you have carbon, bound to 3 hydrogens and 1 oxygen. Okay. And then there's a hydrogen on the other side of the oxygen. Okay. So what we've done is we've just bound the carbon to an oxygen, 1 oxygen carbon bond. All right, so hydrogen is still going to be +1. Oxygen is going to be -2. So for methanol, we have carbon plus our 4 hydrogens, each of which is still +1, plus our 1 oxygen at -2. Adds up to 0 overall. So carbon plus 4 minus 2 equals 0. Carbon for methanol has an oxidation number of -2. Then we come over to formaldehyde, where we have carbon double bonded to oxygen, single bonded to each of our 2 hydrogens. So we keep on going, same as before. Carbon plus our 2 hydrogens. Each hydrogen is +1. And we still have just the 1 oxygen at -2. All adds up to 0. So carbon plus 2 minus 2 equals 0. Carbon equals 0. You might have noticed a trend. You're very clever. Okay. Now we move on to formic acid. Come on. This lag is killing me. All right. All right. So, formic acid. Carbon bonded to oxygen. Oh, wait. And oxygen and hydrogen. I got the formula wrong. CHOOH. Excuse me. Hopefully that won't give you nightmares. All right. Decent. Okay. So now we'll try reconnecting. I'm sorry about this. All right. It is reconnected. Okay. Did I lose my stream entirely? That may be what happened. Sometimes I get, yeah. Okay. All right, so we're back. All right, so where was I? Okay, so formaldehyde. No, formic acid. Formic acid. Formic acid is the acid that gives ant bites their sting. That's why it's called formic acid, from French. Fourmi. It means ant. All right, so carbon plus our two hydrogens. Each hydrogen is positive 1. Plus our two oxygens. Each oxygen is negative 2. Has to add up to 0. So carbon plus 2 minus 4 is equal to 0. Carbon equals positive 2. So our trend continues. And finally, we come to carbon dioxide. Good old familiar CO2. Carbon is now double bonded to each of a pair of oxygens. So carbon plus our two oxygens is what adds up to 0. So carbon minus 4 equals 0. So carbon equals positive 4. That's why we do lectures, Desiree. All right. So that's why oxidation refers to loss of electrons. Okay? Every time you add a carbon-oxygen bond, basically oxygen steals electrons away from the carbon. So carbon starts out, with a nice low oxidation number. Every time an oxygen comes in, it steals those electrons away, meaning that carbon's oxidation number goes up. Electrons have a negative charge, so losing electrons means losing negative charge, means your oxidation number goes up. Okay. The opposite of that is reduction. So as we oxidize the carbon, as we add more and more oxygen bonds to it, the oxidation number on the carbon just keeps on going up and up and up and up and up. So it goes from negative 4 on the left all the way up to positive 4 on the right. Okay. So putting this in redox terms, in terms of oxidation and reduction, carbon over here has been fully reduced. Okay. It has gained as many electrons as it can. Its oxidation number is as low as it can go. Okay. Over here, it has been fully oxidized. Okay. We cannot add any more carbon-oxygen bonds. It has lost as many electrons as it can lose. Its oxidation number is as high as it can go. And the CO2 is fully oxidized. So, hopping back over to our slideshow, I have some examples for you to work through. Go ahead and start working through these while I run downstairs and grab myself a soda pop. Reduction agent and oxidation agent is, yeah, kind of confusing. The reduction agent is the thing that causes reduction in something else. Oxidation agent is the thing that causes oxidation in something else. So for that string of organic compounds, oxygen was the oxidizing agent. Carbon was being oxidized. So yeah, reduction agent and oxidation agent, we throw that in there just because why not be confusing as hell? I am currently writing out this huge list of things with all their oxidation numbers. I will show them to you as soon as that list is done. But for the moment, practice. If you're watching this video later, go ahead and pause and work them out on your own, and then skip forward a few seconds. Meantime, chat, feel free to pepper me with questions. Best way to get in touch with me, I will keep on checking my emails, and I got to remember to get back in the habit of going into that Discord. Sorry about that. All right, so now here are the answers. Most of these, hopefully, are fairly straightforward. The ones I think that will cause people the most trouble are going to be this guy here and this guy here. The oxygen trifluoride and the H2O2, hydrogen peroxide. Okay. Remember, fluorine is always -1, and it always gets its way. So oxygen is almost always -2. Okay. So when it's bound to fluorine, oxygen will do whatever it takes to make fluorine happy. So therefore, oxygen is +3 in the oxygen trifluoride. Coming down to the bottom, we have the hydrogen peroxide. Again, oxygen is almost always -2. In this case, it is a peroxide, and in peroxide, oxygen has an oxidation number of -1. So that's why those two might be particularly confusing. The ammonium chlorate over here, the very last one, that one can be difficult, but only because it has so many atoms to keep track of. Okay. And in the case of the ammonium chlorate, the best way to deal with that, I think perhaps, is to break it apart into its two ions and deal with them separately. Go over the potassium phosphate. Can do, Desiree. So, potassium phosphate, K3PO4. Potassium is the monatomic ion, therefore it's +1. Oxygen is almost always -2. So, our 3 potassiums plus our 1 phosphorus plus our 4 oxygens is equal to 0. So 3 plus phosphorus minus 8 equals 0. Phosphorus equals +5. And now I'll jump down to the bottom of the list and do ammonium chlorate. Like I said, the best way to deal with ammonium chlorate is to break it up into the two ions. So you have NH4 plus and ClO3 minus. So looking at the ammonium, hydrogen is +1. So nitrogen plus our 4 hydrogens equals +1. Nitrogen plus 4 equals 1. So nitrogen is equal to -3. Meanwhile, we come up here to the chlorate. Oxygen is -2. So chlorine plus our 3 oxygens is equal to -1. Chlorine minus 6 equals -1. Chlorine equals +5. So on the test, you will absolutely, positively, necessarily have to do a couple of oxidation number questions, finding the oxidation number of a particular atom in a compound. But the only way to find the oxidation number of any of the individual atoms is to find the oxidation numbers of all of the atoms, each of the atoms, every of the atoms. Okay, you can't really do it any other way. All right, and with that, we have finished this set of slides, and I'm going to take a break. Actually, go ahead and ask some questions. Then I will take a break, go downstairs, grab a snack, and then come back up here in about an hour for the next set of slides. I think I'm going to try and get through 3 today, 3 tomorrow, 3 the next day, until I finish Chapter 8. So I will pause for about 30 seconds to let people type a few questions in the chat. If y'all have any cats on your desks, or if you're looking at this on a tablet or something, you're going nuts. All right. Looks like there aren't any questions, so I'm going to go ahead and call it... oops. Yes, there will be. And yes, I will. They'll be fairly simple. Yeah, don't worry about that. They'll be pretty simple, pretty easy, just to make sure you're paying attention. All right. So we'll go ahead and stop this lecture. I'll see you in about an hour.